We're going to start chapter 2 with these videos, and we're going to break it into 2 sections. What we're working towards is being able to find maximums and minimums, or to use terms, optimization of business problems. Well, what do I mean by that? Well, with optimization of business problems, that's something that as business majors you're actually very interested in. When we make a product, well, how much should we charge for it in order to get our maximum revenue? How much should we charge for it to gain our maximum profit? We'll actually discover that getting the maximum profit may not always be the same thing as finding the maximum revenue. And of course, if we're developing things, producing things, we're always interested in minimizing the cost. And that's what I mean by optimization in business settings. Finding the minimum cost, finding the maximum profit, finding the maximum revenue. To do this, calculus does this very easily and very well. To do this, though, it's important and helpful to know some basics about graphing. And using the tools that we already have. We've learned how to find the derivative and the second derivative. And if we take this and apply some observations about graphing and do a little bit of analysis on our observations, we can use calculus to easily graph and plot a function. And then from this, we can learn how to maximize our revenue and our profit, and also minimize our costs. So the other application, of course, would also be, for example, if you were selling tickets and you knew how much demand you have, well, there should be some way for you to actually calculate from the demand how much you should charge from the tickets. Because after all, if you charge too much, you sell fewer tickets, you lose money. If you underprice the tickets, sell it for too little, well, you may sell more tickets, but you're not getting the maximum profit that you could. So these are the kind of things that we're working towards, and having a solid grasp of the basics, which come from graphing functions, is helpful. So now hopefully some of this stuff will be familiar as you've done graphing in high school. Today's lesson we're going to review some of the terminology, but then apply calculus to it for a quick and easy way of describing graphs of functions. Now, actually when we're doing this, we're going to be looking at sketching functions instead of technically graphing or plotting them. And by that I mean we're going to look at a way of doing it fast. We know it's not 100% accurate, but it's close enough that we have a good idea of what's happening with the function, or in this case, the marginal, or the cost, or the revenue. So if we were going to publish this, we'd want to find a good program to actually put the formula in correctly, but we can graph it very quickly and know that it's 90 to 95% accurate by sketching it, and spend very little time doing this. Now, why would we be interested in doing this kind of thing? Why would we even want to sketch a graph? Well, sometimes a picture of a curve is more helpful than the equation itself is. If we can visualize what a graph is doing, then we can make better decisions in situations. For example, let's say you're walking around the production area of your company, and the foreman comes up to you and asks, we're behind in our production on this project. Should we speed up our production, or should we simply be late in delivering our current contract? Well, if we can picture what our cost and revenue functions are, well, then we have an idea what we should do. If we look here, if this is our normal cost function, as x gets greater, of course, it increases. If we know that this is what it is, or if we could take our cost function and quickly sketch it on the clipboard that we're carrying around with, or a piece of paper somewhere, well, then we can know that this is what our normal cost function is. And if we speed up production, well, that means our costs are going to increase. So we could imagine, by sketching an increased cost function, the red function, that now the costs are going to be a little bit higher for the same amount of products delivered, but that means we're getting it done faster. So originally, if we were here, it would cost us this much to do it, but because we're putting in maybe overtime or paying for an extra person to come and help, our costs are now this much. And whereas in our original function we would pay this amount, our y value would be here. To speed up production, would, again, getting more help might mean that we're actually going to cost this much money. So our costs have increased. Well, if we want to know, we know our costs are going to increase, but we'd have to compare this to our revenue function. Well, again, if we know what a revenue function is, either in terms of x, either in terms of x, then we can sketch it quickly, graph it quickly, or if we just simply know, because this is our business, maybe our revenue function looks a little something like this. And so as x increases, of course, our revenue increases, but at some point it starts to come back down. So if the green line is our revenue function, we can look at it and say, well, Mr. Foreman, we should increase our production. And if we look at it and say, well, if we need to produce X amount of goods, our cost would usually be this. Our revenue function would be here. So normally this whole thing would be our profit, our revenue minus our cost. But in this case, if we speed up production, our cost will be here. So we're still going to make a profit because the revenue minus our cost gives us this amount of money. It's not as much as it was before, but we can stay on time. This would be important, for example, if there was a clause in your contract that say if you have late delivery, there's a fee or a penalty invoked because it's late. And some businesses function that way. So in this case, we know by increasing the production, increasing our cost of production, we will still make a profit and we won't have any fee or any penalty implied. So we wouldn't want to go ahead and do that. However, if we realize that when we're doing this, that if we were providing this many units, well, if we speed up our production, it's going to cost us this much and our profit is this much. Well, let's see, even on here, it's really hard to see. In this case, do we want to speed up our production? Or what if we were looking at a value here, when x is this value, our cost would normally be this, now it's this, and our revenue function is the green line. So again, when we would have made a profit, it would be this much. But now, because if we speed up our cost, this amount of money we will lose. Our revenue function is here, our cost function is here. We take the lower one and subtract it, we would end up losing money. So in the case out here, we would tell our foreman, no, do not speed up production. The only other thing to take into account, of course, would be if there's any kind of fee that could make us decide that, well, the fee's large enough that we do want to take the loss anyway. But in this, if you don't have to worry about a fee, in this last case, we would tell the foreman, no, don't speed up production, because if we do that, we're going to lose money, versus if we are just late, we will still make some profit, even if it is small. So having an idea and being able to do this quickly is a helpful thing. It can be a helpful thing in business. Of course, maybe when you go back to your desk, you want to sit down, plug the numbers in the computer, and make sure that everything comes out right. But you could give your foreman a snap answer right away, and he knows what to do. And it won't cost your company any extra funds. We're going to go over some of the basic terminology. From this, I'm expecting that you'll know the terminology and be able to use it, which also means that if you're looking at a graph, you can describe it and say what it is using the terminology. Now, if we look at this particular function, we realize that the graph is always going up. We would say the y value is always rising. Our f of x, the value when we put x's into f of x, always goes up. And just a reminder that we always read the graph from left to right as we're looking at this. So the y values can continue to get bigger and bigger. So in using the math terminology in English, we'd say that this is an increasing function. And the function continues to rise throughout the entire section that we can see. So again, it's an increasing function. Now, mathematically, we would write if x sub 1 is less than x sub 2, let me move the mouse there, that means if the one value you have of x is less than the second value you have, So let's just say it was x sub 1 was here, and x sub 2 was here. Well, if that's the case, then that means that the y value, or your f of x value, at the first, when x is equal to this one, is going to be less than the y or f of x value at the second point, which is greater. So it's always going to continue to go up. And as we talk about this, we would simply say that f of x is increasing at this value, at x is equal to whatever it may be. So it's not too hard. It kind of makes sense. The function's increasing. As we draw it, it always goes up. Now, to figure this out, we oftentimes need to look at the values right around the value we're looking at. Because if we look just at a point and don't compare it to anything else, we don't know if it's going up or down. So in looking at the values around it, we can look at it and say, oh yeah, it's increasing at c because it's increasing over the interval that includes c. Now here we have a function where obviously it's going down, and we'd say it's decreasing at x is equal to d. The same logic applies. The values are going down, and you look at the values around d to decide, is it going down? So the graph is going down. It's declining over the marked interval. And so, as I'm sure you've guessed, we call this a decreasing function. And we say that it is decreasing while it continues to decline. As you can guess, it's possible for a function to increase and then decrease later. And that's why we have to look at the intervals around it. And using the mathematical formula, or the mathematical definition that we were using, if again your first x value is less than your second value, then your y value, or your f of x value at the first f of x value at the first x will be greater than the y value at the second x, or the larger x, or the f of x value at the second point. And as you also assume, or as you also guessed, we would say that f of x is decreasing over this range. So for example, up here, again, f of x is increasing over this range at this point c, but it's over the entire range, and is decreasing here at x is equal to d, and all the points around d, all of these values here. Now in the third graph here, we notice that it says it's at c here, it's neither increasing nor decreasing. Obviously, if we look at it, just by looking with our eyes, we see, well, this is decreasing, and it decreases to this point c, and then after it increases. So we'd say it's not increasing or decreasing because it's changing from decreasing to increasing. And this is something that's called a minimum, and we'll see this very shortly. It is something that we need to use, and it's helpful in calculus for graphing. Now, a relative maximum or minimum would be, well, looking at each case, a relative maximum would be where the graph changes from increasing to decreasing. Well, okay, an example of that would be, here we have a graph, and we realize that to this point when x is equal to a, the function is increasing. After this point a, the function is decreasing. So we look at it and say, oh, well, yes, it's a maximum. It's the y value here is going to be the highest, so it's the maximum. So we'd say that we have a relative maximum at x is equal to a. Here, we would have a relative minimum. And again, a minimum is where the graph changes from decreasing to increasing. So hopefully this makes sense. As we look at this graph, the function is decreasing until it gets to a. After a, it's increasing. And we notice that in both of these cases, that if we took the slope at x is equal to a, what would be a horizontal line? What's the slope of a horizontal line? It's 0, right? The y value is not changing. The change in y over the change in x. And it's the same down here too. So we realize that where we have a maximum or minimum, the slope is equal to 0. And of course the slope is the first derivative. So the first derivative will be equal to 0. But we'll come to that again in a future class. Now, there's also something called an absolute maximum and an absolute minimums. And as you might guess, they are the same things. The absolute maximum, however, is going to have the highest y value of the entire graph. And the absolute minimum will be the absolute lowest value of the graph. So in this case, when we're looking at this, we can have a maximum and minimum together. As we're looking at this particular point, we realize, oh, okay, here there is a minimum. That it's decreasing and then it's increasing. So this would be considered a relative minimum, because this one is the absolute minimum. It's the one that is absolutely the lowest. So with the absolute minimum, it's this one. Over here, we'd say that we have a relative minimum. In this case, we do have an absolute maximum here because the y value is not any higher anyplace else. Over here, we can look at it and say, because x isn't defined as when it's negative, it's starting from this point and going on, and for the section that we can see, we say, well, this is the lowest value. So in this case, it's actually an absolute minimum value because it doesn't go any lower than this value. But there is no absolute maximum value. Here there's a relative maximum value, but we can't say that there's an absolute because the graph continues on. Over the section that we can see, we would say that this point here would be the absolute maximum. But if we assume that the graph continues, we can't say that. So this graph, we could say it has a relative maximum, but we can't define the absolute maximum if we're continuing the graph beyond this section. If we are stopping it here, then we can say that we have a relative maximum here and an absolute maximum. Again, it depends on how it is defined. Now, increasing and decreasing slope. Oftentimes students confuse this with an increasing and decreasing function. They are two separate things. Sometimes a graph is increasing and the slope is increasing, but it's possible to have a decreasing function where the slope is increasing. So we'll have to look at this, and of course it works vice versa too. But first, what is an increasing or decrease? What is increasing or decreasing slope? Now when we're working with increasing and decreasing slope, we are looking at the slope itself. So if we look at figure 8, if we look at the slope at any particular point, let's choose one of the higher ones here. If we were to draw the tangent line in, it would be something like this. And we can look at it and say, well, the value of that would appear to be, oh, I don't know, maybe it's minus 1/2. It's going down. So let's say the slope here is at minus 1/2. Well, if we took the slope here, we'd say, well, the slope, well, I didn't draw this extremely straight, but more or less we could say the slope is here at minus 1. So the second one is at minus 1. And if we took the slope down here, we can look at it and say, well, the slope for that, it looks like that may be about minus 4. So it's out here at minus 4. Well, as we read this from left to right, the slope would start at minus 1/2, go down to minus 1, keep decreasing to minus 4, and the idea is that it keeps decreasing and it gets steeper and steeper. Since the slope is less steep to start with, and it gets steeper and steeper, we would look at this and say, oh, it's becoming more negative. The value of the slope is becoming smaller and smaller. Minus 1 is bigger than minus 4. Minus 5, if we looked at the next one, would be smaller than minus 4, so it's decreasing. So in this particular function, the entire function, just the blue line, it is decreasing, but the slope is also decreasing when we look at this. Now, in figure 9, we look at it and say, oh, well, here, the function, the blue line, the function is decreasing here too. But what's happening with the slope? If we drew the tangent line out about here, so well, that would appear to be somewhere out around maybe negative 6 out here at this point. And if we took the slope maybe here, well, that would appear to be about here at minus 2. And if we took the slope in here, well, that may be roughly like minus 3/4, more or less. Well, we're starting from left to right at minus 6, and we're increasing to minus 2 to minus 3/4, and potentially continuing on. The graph stops here, so maybe stops here, we don't know where it is, but the values from left to right of the slope are increasing. So while the function, the blue line, is decreasing, the slope is becoming less negative. It's increasing. It's going from -6, -5, -4, up towards 0 at this point. So the slope is increasing. So try to keep the two straight. It's always think about the function itself as increasing or decreasing, and then look at the tangent lines. What's happening? In figure 9, they're going from more steep to less steep to less steep to less steep as it goes, so the slope must be increasing. The values are becoming less negative, they're increasing. Now concavity is looking at the slope again, and it's saying if the blue line, of course, would be the graph, and if we drew the tangent lines for this, the tangent lines would all be below the graph in this case. If we draw the line here, the tangent line's here, they have another one drawn here. Even if we drew it here, the tangent line would be below the graph, or the graph would be above the tangent lines. Well, this is how they define something being concave up. The graph is above the tangent lines over this section. And if we look at the slopes, we realize that when it is concave up, the slope increases. So here it's maybe, say it's positive 1/2. Here the slope may be 1, here the slope may be 2, kind of thing. The slope is increasing as we go. Now in reality of it, one of the easiest ways to remember this is that when it's concave up, the graph opens upward. So if we look at this, if we continue this graph, it would go up here, and maybe it would continue on over here into this kind of shape. And you realize that the lowest point, it gets wider and wider as you go up. So you get this U kind of shape, or a cup kind of shape. So that's concave up. When it's concave down, technically the definition is that the graph is below the tangent lines over these sections, and that the slope will decrease. Here it's steeper, and here it's less steep as you go along here. But the easy way to remember it again, if we were to continue this, we'd say that it's like an upside down cup. It's concave down. The high point is up here, and as you move out from it, it gets wider and wider, so it's concave down. It opens downward. An inflection point would be between the two. And we can have a graph that is concave up. And here's an example where it's concave up, even if we continued the graph over here, but looking even just at this section, it's concave up, and then from here we notice it's concave down. We notice at this point, and this is the point where we call it a point of inflection or an inflection point, it's where the graph changes from concave up to concave down, or the other way around. In an earlier section, we said sometimes when you draw the tangent line, it has to go through the graph itself, the curve that you're graphing. Well, whenever it goes through, that's going to be the inflection point. Before it, here it's concave up, after it, it's concave down. And this one, it's concave up, and it changes then to concave down here. And the third one, it's concave down. And once you get past this point, it's concave up. And here, at these points where it changes, we don't say that it has concavity because it's an inflection point. It's not concave up, it's not concave down, it's an inflection point. Now, using all of this information, how would we describe this graph? Well, let's look first for when x, if we look from 0 to 3, when x is from 0 to 3, but not including 3. Well, as you might guess, the function's going up, so it's going to be increasing as we do this. And hopefully that makes sense. And if we wanted to use some of our other terminology, would it be concave up or concave down here or along this section? Well, if we drew in the tangent lines, they're always going to be below, or from the high point it opens downward. So we'd say that it's concave down. What's happening with the slope here? Well, the slope is pretty steep here, and it's less steep here, and less steep here. So we'd say that the slope is decreasing. It's becoming less steep. The values are getting smaller and smaller. So when x is less than 3, we'd say that the function is increasing and concave down. And as far as the slope is concerned, it's decreasing. Now when x is equal to 3, how would we describe this? Well, yeah, it's a relative maximum. It looks like this could go on higher and higher, so we can say that it's a relative maximum. But if the graph stopped here, we could even say it's an absolute maximum. But we can clearly say that it's a relative maximum. It is a maximum. And if it's a maximum, is it concave up or down here? Well, it's concave down. Concavity is all along the line. The only place that you don't have concavity is where the point of inflection is, where the inflection point is. So from here, it's also concave down. Now what's happening with the slope here at this line? Well, again, it's a horizontal line, so the slope will be 0. So at x is equal to 3, there's a relative maximum. We also know that it's concave down, but a relative maximum would tell us that it is concave down, because that's the only way we can have a relative maximum is if it's concave down. And the slope is 0. Now, for between 3 and 4, what's happening? Is it increasing or decreasing? Obviously, it's decreasing. Now, what's happening with the concavity? Is it concave up or down? Well, it's concave down, right? If we drew in all the tangent lines, the graph would be below. But again, we think of it the high point here, and all along here, it's opening downwards, so it's concave down all along this section. And what's happening with the slope? Well, obviously, it's negative, right? But here it starts kind of, well, it's not flat because we can't include this point, but it's a little bit negative, a little bit more negative. The line gets steeper and steeper as it comes down, so we would say that the slope is decreasing. And between 3 and 4, the function is decreasing, it's concave down, slope is decreasing. When x is equal to 4, well, we kind of already gave that away, right? It's a change of concavity. If we draw the tangent line is below here and above here. It's a point of inflection. And we'd say that there is no concavity there because it's a point of inflection. It's not concave up, it's not concave down. And if we're looking at the slope, there really isn't much we can say about it there. If we extended the tangent line, we could define what it is, but that'll be different for every particular graph. So we can't say that the slope is increasing or decreasing there because it is decreasing, becoming more negative as it comes down, and after that it's becoming less negative, so it's changing. So we can't say that the slope is increasing or decreasing. Now, what about for between 4 and 5? Well, the function is still decreasing. And what about the concavity? Well, we'd said here it changed, right? Now if you drew the tangent lines, the graph is above it. So if this is the low point, we realize it's going to be concave up from this point, not including 4, but from 4, the rest of the way. So we'd say that between 4 and 5, the function is decreasing and it's concave up, and we're going from more negative to less negative to almost to 0. That happens at 5. So the slope is increasing as we go. Now, when x is equal to 5, we realize, well, the slope is 0, so we have that part already, and it's changing from decreasing to increasing. So that must mean that we have a relative minimum. And of course, as we said before, from this point of inflection, and as long as it continues to open upwards, it's going to be concave up. So when x is greater than 5, we can say that the function is increasing. It's still concave up, and the slope is going to be getting greater and greater. So we'd say that it's increasing. It goes from less, not very steep here, to more steep, to very steep, and it keeps increasing as we go. So when x is greater than 5, the function's increasing. We know it's concave up, and again, the slope is increasing. So this is the kind of thing I would expect you to be able to do in the homework and on any test or quiz, looking at a graph and be able to say what it is at particular points. and also to be able to go the other way, but we'll learn more about that. Actually, the homework will help teach you that. If it says that there's a relative maximum here, well, could you draw a quick sketch of it to get an idea of what it would look like? Now, in doing this, do all graphs have an x and a y-intercept? Well, of course, if you remember your high school math, you say, well, no, not all of them do. Here's an example where we do not have an x-intercept. An x-intercept means, does it cross over the x-axis here anywhere? In this one, it does not. Does it have a y-intercept? Yes, it does, because it crosses the y-axis, and it crosses the y-axis here. So it has a y-intercept. So this particular function, y equals x squared plus 1, we'd say it has a y-intercept, but it has no x-intercept. It doesn't cross the x-axis. With this particular graph, we're working with the square root function, and we're looking at it, oh yeah, this has a x-intercept because it has a point right here, but it has no y-intercept. So we can define it that way. The graph graph exists that we have no y-intercept, but we do have an x-intercept, even if it's only at one point. Now, whenever we're doing this, the x-coordinate of the x-intercept is often called the zero of the function. Like here, at x is equal to 1, it's referred to as the zero of the function because our y value is 0 at that point. Wherever it crosses the x-axis, the y value is going to be 0. And in math, these are important terms, the zeros of the functions. In business, you're interested in that because it's possibly where you're going, if you're looking at profit, in this case, it's where you're starting to make profit. Or if it was coming down and crossed the axis and went negative, you'd want to know that point because that's the point where you're going to start losing money. And you don't want to have that happen. So if you see this in the book, it is more of a math term, so I won't use it so much in class. But when the book talks about it, you'll know what it is now. Now, here are two functions, and the first one has no x or y intercept. It's a graph of y equals 1 over x, and we realize that it doesn't actually touch the y-axis at all. And when that happens, when it gets really, really close, we could even say it gets infinitely close, but doesn't actually touch, then we would say that it's an asymptote. We have the same thing on the x-axis. The graph comes down, it gets closer and closer, but it doesn't actually touch the x-axis. And here it's coming up, it gets really, really close, but doesn't touch. Over here, again, we have a square root function, and this is a case where you have both intercepts, the x and the y-intercept, at one point, at 0, 0, and 0, 0 is also known as the origin, of course. So it's possible to have both of these. Now, we'll also talk about undefined points. Undefined points could be where there's an asymptote, where you don't have a particular point in a function, but it's a point where the function or the particular graph is not defined. So if, again, we go back to this, our graphs here, we can look at the graphs of y equals 1 over x, and we realize that it's not defined when x is equal to 0. There will be no point. For any other x value, there is a y value, and there will be a point, but it will not be for here. So we would say that we have an undefined point at x is equal to 0. Over here, we realize when x is 0 and when x is positive, we will have points, but we have an entire undefined range when x is less than 0. Over here, there's nothing. It's not defined at all. So we would say that in this function, the square root function, it is undefined for x when x is less than 0. It has an entire range of undefined points. Asymptotes I've already talked about, but just an idea here are some horizontal asymptotes. And this one's even considered horizontal, even though it's more diagonal. But it's still considered horizontal. When we're looking at these, with horizontal asymptotes, by definition, it's where the y values approach a specific value, but they never actually reach it. If this up here was 300, we know that the values as you move out here, the value for x will get close to 300 but never touch it. In this particular graph, we would look at it and say, well, the values are coming down, and if this is, say, maybe 50 here, the values are coming down towards 50, but they'll never actually touch it. And in this particular case, we look at this and it's like, well, for 1 unit over, we go up 1, over 1, up 1. Well, this line, we could look at and say, well, it has a slope of 1. This would be y is equal to x. If that's the case, the y values start here, and they get closer and closer to this line where y equals x. So we would say in this case that the horizontal asymptote is that y is equal to x. Here we'd say that y is equal to 300. The asymptote is at y equals 300. Here we'd say that the asymptote is as the value of y approaches the value of x, but it never actually touches. So the asymptote is at y is equal to x. It's a little bit strange, so we won't do much with this, but just to be aware of it when you see it in the book. Horizontal asymptotes are calculated by determining the limits. We didn't really get into this, but this terminology simply means the limit of the function of f of x as x approaches infinity. So what is this limit? Well, the limit is here, again, if this was 300, the limit is 300 here. It's approaching this value of 300, even though it never touches it. Now, the limits can also be, depends on which way you're going. With these, we're approaching positive infinity. With 1 over x, if we go back to our graph, as x approaches negative infinity, we would have a different value over here. So when we're working with this, another way of determining the limit is to say the limit of the function f of x as x approaches negative infinity, as it goes down to negative, really, really large numbers. And if the limit actually exists, the value of the asymptote is the horizontal asymptote. So again, if this was 300, the value of the asymptote would be 300. The value of the asymptote here, you could say is y is equal to x to be clear, but you could simply say that the value is x. And if we have vertical asymptotes, if we go back and modify our 1 over x thing to be 1 over x minus 2 for our function, a vertical asymptote is going to go up and down. The values will approach it but never actually touch that vertical line. And usually it's the result of dividing by 0. The kind of thing we're told we can't do, so to speak. And when we're working with this, again, it gets really, really close. We'd say that it gets infinitely close to this, but never actually touches it. And again, that's a vertical asymptote. Now, the terminology that I've introduced is something you should be aware of and understand when I talk about it, when you see it in the homework, when you do it in an exam, so you can see the words and maybe draw a quick sketch from it. Or you can look at the sketch and say, oh, here's the absolute maximum, here's the relative maximum, here's the point of concavity, to be able to go from a graph and go back to the terms in English. That's what we're getting from this section. We'll start to apply calculus to this in the next class. The homework for today, again, we're starting chapter 2, section 1 of chapter 2. Here's the homework problems. And for this graphing or sketching section, in the first class we went over this graphing transformations, if you stayed for it. And I have it on Moodle here as well. It could be a good review, because we'll get into using it more heavily over the next week or so. So you can review it again if you wish. Again, all of the homework is on Moodle, so you can get it there as well. And of course, you can look at the answers in the back of your book or in the answer book that's on Moodle as well to assist you with that.